Good evening. We are continuing our easy lecture series on essentially theory, background, and implementation and examples for modeling and simulation, realistic modeling and simulation of earthquakes, soil structures, and their interaction. Today with me are again Dr. Han Yang.
Hello.
And Mr. Heshen Wang, will talk
Hi.
today about stochastic elastic plastic finite elements. These recordings are going to be posted online and we'll make them available through lecture notes and through our website. My name is Boris Jeremic, and today is Thursday, May 14th, in the middle of quarantine. So again, I'm in Switzerland, in Zurich, and Heshen and Han are in Davis, California. All three of us under semi-lockdown. So Heshen, please share your screen and let's start discussion. Let's start this session. Okay, thank you.
Okay, yeah. Okay.
Good,
so
great.
Yeah, good morning everyone. So today we're going to continue to talk about the uncertainty quantification using Galeckin's stochastic finite element method. And this is the outline of our talk. So again, we're going to start with the introduction of the background of this uncertainty quantification. So as we mentioned before, so now we have uncertain system equations, and where we have the uncertain stiffness on the left-hand side, and also we have an uncertain forcing term on the right-hand side. And the whole system will give you uncertain displacement, velocity, and acceleration. So
I'm sorry for interrupting.
Yeah.
If I may just add, we assume that mass matrix is very certain. We should know that. And we also assume that the viscous damping is certain, although we can make it uncertain. But in this case, most of the dissipation, most of the uncertainty really comes from the stiffness. So we make an assumption that the stiffness is very uncertain, whatever it comes from the material testing. And the actual loading, which is actually earthquake because we go through DRM, is uncertain. So with that, it becomes left-hand side is the stiffness, right-hand side is the loading. And that's where the two main uncertainties are. Yes, please go ahead.
Yeah. And for this uncertainty quantification problem, we have two tasks. Number one is the uncertainty characterization. Essentially, we need to characterize what is the statistics and what is the distribution, what is the correlation of your uncertain stiffness and uncertain force. And in our previous two lectures, we already talked about the Hermite polynomial chaos Cahunen-Loewe expansion to deal with this uncertainty characterization problem. So now we can quantify or characterize our stiffness and our force in terms of the Hermite polynomial chaos. So today we're going to talk about the second part, which is the uncertainty propagation part. Essentially, we need to solve this stochastic partial differential equation and find the probabilistic dynamic response of the displacement in terms of its mean, variance, PDF, and its correlation. And for the problem, the uncertainty propagation, we have two main types of the method for doing that. Number one is so-called the non-intrusive method, including Monte Carlo method, stochastic collocation method, and so on. So this method are named as a non-intrusive method in terms that they need no modifications to the underlying deterministic solver. So this is a good advantage. It relies on the repeatedly deterministic sampling of the uncertainties to quantify the probabilistic response. However, it has a very slow convergence because of this Monte Carlo simulation method. You know, the convergence rate for Monte Carlo simulation is 1 over square root of n. And it's very computationally demanding to get a very accurate probabilistic response. And especially it's hard to get a very stable tail distribution. And we know, for example, in some applications, for example, seismic risk analysis, the tail distribution is really important that control the risk. And on the other hand, we have another type of method, which is called intrusive method. Yeah.
Before you continue, I'm sorry. So yes, they're slow and they're very inaccurate. They're inaccurate. And you remember there was a conference last year, 2 years ago, when that fellow from SCAC said that if they do simulation of the LA basin probabilistically, and they try to get some probabilities of motions, it's going to take them 300 years. 300 years because they have to repeat simulations that last for a few days, and they need to be repeated and repeated, you know, by changing parametrically properties and so on and so on. And he said that the estimate was that it's going to take 300 years. This is the method you're going to show is really needed because it solves a lot of problems in that previous approach with the non-intrusive methods. Yes, go ahead.
Yeah, that's true. Yeah, that's why we try to change to the intrusive method. Yeah, for intrusive method, you need to modify the underlying solver. So now you need to directly solve the stochastic partial differential equation, in your implementation part. And for the intrusive method, for example, we have the perturbation approach, we have the stochastic Galerkin approach. For the perturbation approach, it is essentially based on the a Taylor expansion of your uncertainties in the probabilistic space. However, it only works for very small uncertainties because of the nature of the Taylor expansion. It will become very inaccurate when you have a large coefficient of variance in your uncertainties.
Yes.
And while for the stochastic Galerkin approach, we represent the uncertainties by the orthogonal Hermite polynomial chaos. Essentially, we are introducing an additional layer of the discretization in probabilistic space now. And by the Galerkin projection, it guarantees the error optimization and optimal convergence. So yeah, so this is the approach that we are presenting
Good.
here.
Yes.
Yeah, and so let's start with the stochastic finite element method. So again, now we have the unknown displacement random field in space, time, and probabilistic space. So first step, we're going to perform a discretization in spatial domain. So using the conventional shape function as the deterministic finite element. So now we represent this unknown displacement random field with a deterministic shape function and also the uncertain nodal displacement. So this is a standard spatial discretization as a deterministic finite element method. So and then we can perform the polynomial chaos Cahutan-Loiva expansion of this uh, unknown of this uncertain nodal displacement. So with this formula. So this is the additional layer of discretization in probabilistic space. And with that, we will get the deterministic polynomial chaos coefficient of this unknown nodal displacement. And we represented it with the multidimensional Hermite polynomial chaos. And when we combine this together, we will get the get this representation for the unknown displacement around the field, and it has been discretized in both space and the probabilistic space. Yeah. Yes.
So if you think about it, it's like you remember for finite elements we have nodes, and then let's say you have two nodes. Between those two nodes, we assume shape functions. So if we know displacements or whatever the degree of freedom is at this node and this node, we can find anything in between because of shape functions. Now our nodes have been expanded into probability space. So our node is not just a deterministic one displacement. It's a whole series of displacements in probability space. And then we say that in between, we can also find out all the uncertain displacements by looking at the uncertain displacements at nodes and then using the same interpolation functions for all the probability spaces in between.
Yeah, that's true. Yeah. And then we combine this representation of the uncertain displacement random field with the Galerkin weak formulation of the stochastic partial differential equation. We will get this formula. And here the Bnx is the shape function gradient as the deterministic finite element method. And in here we can see we have the uncertain stiffness term. This can be a 1D, can be elastic or elastoplastic.
Yes.
And also we have an uncertain forcing term represented here. Yeah. So we need to perform the characterization of these uncertainties, of this uncertain stiffness term and this uncertain forcing term using the Hermite polynomial chaos Cahutan-Loiva expansion as we presented before. So now we can get this expansion in probabilistic space. And then we combine this expansion with the weak formulation that I shown in previous slides. Then we can get this expanded weak formulation in probabilistic space. So this is still like an uncertain equation because we have this polynomial chaos here.
Yes.
It has polynomial chaos here. Yeah, so we cannot directly solve such a uncertain system of equations. So instead of doing that, we need to apply the Galerkin projection. Essentially, we apply we multiply both sides by the polynomial chaos basis phi j, and then we take the expectation. So once we do this Galerkin projection, we can get a deterministic spatial probabilistic discretized Galerkin projected system equations. So as you can see here, we still have the mass, but this is not a conventional mass. It's a expanded, stochastic expanded mass matrix, where you have you still have a deterministic mass matrix, but combine this deterministic mass matrix with the double product of the polynomial chaos. And also you will have a stiffness term. Again, this is not a conventional deterministic stiffness. This is the expanded stiffness stiffness matrix, where you have a deterministic stiffness, combine it with the triple product of the Hermite polynomial chaos basis. And similarly, you have a expanded forcing term. And in this and this becomes a deterministic ordinary differential equation of the unknown deterministic polynomial chaos coefficient of this unknown displacement, of this uncertain displacement. And in order to construct all of this expanded mass and stiffness matrix, we're going to need the expectation of the double and the triple product of the polynomial chaos. And yes.
No, no, go ahead after you're done. Give me just to talk a little bit more about this.
Yeah, and generally we will this can be numerically evaluated, and we can pre-compute it and store them as a database, and then we can query them when we construct this mass and stiffness matrix. Yeah.
So essentially the system is very similar looking, except that now it's expanding to probability spaces. So what you're solving for are coefficients of probability space expansion of the degrees of freedom. So the system becomes larger, that's true. It becomes much harder. I mean, it depends on how large the system becomes, depends on how many PC terms, how many KL terms you have. But you solve in one shot. In each time step, you solve for those coefficients, and you can reconstruct full PDF of everything, displacements, velocities, accelerations, and from there strain and stress and whatnot. So full probability distribution functions very accurately obtained for all these unknowns.
That's true. And yeah, then we can get this expanded system equations that are equivalent to the original stochastic partial differential equation. And we need to do a final additional discretization in time domain. So because of this is the stochastic ODE, so we can do the discretize in time domain, and then it can be solved by any dynamic integration scheme. For example, you can use the Newmark beta method or Huber-Hughes-Taylor alpha method to get the response of each time step. Yes. So as I mentioned before, in order to construct this mass and stiffness matrix, you need two parts. Number one is a deterministic mass and stiffness matrix, and number two is the double and triple product of the polynomial chaos. And for the polynomial chaos of the uncertain displacement field, the dimension of such a output of the uncertain displacement should equal to the summation of the both the PC dimensions of the stiffness and the PC dimension of the force, because both of these parts, they will influence the output. So the uncertainties of the displacement should incorporate both of these uncertainties. Uncertainties comes from the stiffness and comes from the force. And the order of such a displacement should be greater than both the stiffness and the force term.
Yes.
And yeah, so this whole formulation for the general stochastic FEM might be quite complicated. So now I'm trying to show you a very detailed, very simple but detailed example of how to do this Galerkin projection and and the formulation.
It is complicated first time you see it, and then you spend a few years, and you spend more than a few years, it becomes really easy. Go ahead. Just like everything in life.
Yeah. And say let's start with a deterministic static single degree of freedom equation. So this is just a single equation, and now we try to consider the uncertainty in such a system. Say we consider the uncertain E, and which is the stiffness, and we're considering the uncertain force on the right hand side. And again, the first step, we're going to perform the uncertainty characterization. We perform the polynomial chaos Cahulian-Loiva expansion for both of the uncertain force, uncertain stiffness, uncertain force, and the uncertain output, which is our displacement. And we combine this with the original uncertain system equations. We can get this expanded uncertain equations. And now we have this polynomial chaos basis in the system, so we cannot directly solve it. So we solve it by by doing the projection. So again, we multiply both sides multiply polynomial chaos spaces on the both sides, and we take the expectation. So then the whole thing will come down as the deterministic system of equations. So in this index notation. So I think it might help to write this index notation into the matrix notation so that you can know how the stiffness is constructed, how the force is organized. So when we write this index notation into the matrix notation, we can get this expanded expanded system equations in matrix notation. As you can see here, so the original single deterministic deterministic equation. Once we consider in the uncertainties, it becomes an h by h larger expanded matrix of a system. And this h here is the number of the polynomial chaos terms in your uncertainty displacement. Essentially, the single degree of freedom that we are solving in the deterministic problem now becomes a h term, become the in total h terms in the probabilistic space, and the whole system becomes h times h larger. Yes. Yes,
Can I say something for a second?
Yeah.
So essentially, what you're solving, it was a single degree of freedom system, but now that single degree of freedom was expanded into probability spaces. So what you're doing now, you're essentially solving for coefficients in those probability spaces. And once you get those, you can recombine them and get back the actual probability density function of the single degree of freedom for the full PDF of that. And that's why the system grows to h times h. So it grows quite a bit, can grow quite a bit. But again, you solve this in one shot. There's no need to repeat and so on, and can be solved very efficiently, and it's very accurate. Yes, go ahead.
And the above formulation is already complete for linear elastic problem. However, for the nonlinear problem, we still need the probabilistic constitutive modeling part to close the loop. And presenting here is a hysteretic Armstrong-Frederick nonlinear kinematic hardening equation. This is a deterministic constitutive equation, and we have applied this equation to modeling the hysteretic behavior between the restoring force and the interstory drift, Fr and eta. And here and the CR are the model parameters. And so now, if we want to consider uncertainty in such a probabilistic, in such a deterministic constitutive relation, again, we need to characterize what is our input parameter uncertainties in HA and in CR, and represent them into Hermite polynomial chaos. And then we combine this polynomial chaos representation with the original formulation of our constitutive driver. Then we can, and we perform the Galerkin projection, we can get this modeling equations where we can get the probabilistic updating of the increment of the restoring force and the probabilistic updating of the uncertain stiffness term. And here I'm showing you the the probabilistic response of the hysteretic behavior calculated by Monte Carlo simulation and calculated by this direct probabilistic constitutive modeling. As you can see here, they are matched pretty well. And but please note that in this case, actually the constitutive directly by polynomial chaos and the Galerkin projection is at least 1,000 times faster than the Monte Carlo simulation. Yes, Professor. Yeah.
So essentially, what you're using the famous Armstrong-Frederick kinematic hardening model, but we're really looking at the shear element and 1D propagation. And so what you're showing is the force versus the shear, what you call interstory drift. This is not used for frames, but so essentially a 1D element that has a shear force and shear deformation. And we use this Armstrong-Frederick equation that turns out to be a very useful equation. And what you can do with this equation, you can provide uncertainty of the initial stiffness, the HA, and the plateau, the horizontal asymptote. This is HA over CR. And if you characterize those two as uncertain as probabilistic parameters, which you can do from tests, you do multiple tests on a material, you essentially end up with an equation like this. And what you show here is for that single element, you did the verification with Monte Carlo, and our solution is excellent. It's matching right there with Monte Carlo, but it took Monte Carlo 1,000 times longer to do this, because you need a lot of these repetitions. And so we are
Yes.
1,000 times faster and as accurate. And so, yes, please go ahead.
Yeah, so this is very useful, and in the next lecture, I will show some practical examples of how
Yes.
to apply this method to the wave propagation and also to
Yes.
the nonlinear SEPFEM structure in the risk analysis.
Yes.
Yes. And with that, I will give thanks to my collaborators and funding resources, and also you can check our implementation in the real ED system if you want to use that. Yeah.
Thank you very much. So why don't you just
Thanks for
get
your
out
attention.
of the screen sharing part. So thank you very much. So next time we're gonna actually show one of those examples where we have maybe a single stack of elements or single frame with
Yeah.
few floors, and
Yes.
and we're gonna look at wave propagation essentially in 1D. We're working on the 3D. We have a 3D solution from Fokker Planck, but that's too complicated and too slow. So we're trying to get this in closed form so that you are able to propagate full 3D waves, nonlinear 3D waves, so that your solution, every displacement, every degree of freedom is going to be given as a full PDF. So with that, I'll thank you. And just to announce, we're going to continue with this. And a few days from now, we're going to continue, maybe even tomorrow on Friday. We're going to continue recording and giving you some more material. As Heshan said, this is all implemented already in Real Easy. It's in the lecture notes. We still need to put in the DSL manual, we still need to put some of these commands in there, but that's going to happen over the next few days. So with that, thank you all very much. I'll stop recording right now.